Trevor, Dhananjay Mohan, and Kushal Dey. So the Himalayas themselves, as we just heard, are characterized by steep elevational gradients, more than 8,000 meters between low and high elevation sites. And along that gradient, there are steep climatic gradient as well. So low elevation sites are characterized by warm, humid environments, and the high elevation mountain peaks are arid and very cold. So along this gradient, climatically and elevationally, there's a lot of turnover in species identity, but there's also an axis of variation that we just heard about along the geographic plane as well. So the southeast in red is characterized by, again, these warm, humid environments, but it's more arid and cooler and more seasonal in the west. So if we look at the patterns of species richness along this elevational gradient, in both places we see that there are many more species in the east, and Trevor just told us that. So there are 40% more species in the east than in the west. And these relationships can be explained by two factors. Essentially, we either have local conditions driving the richness of species within these two regions, or potentially, so in the case of the east, potentially there are more resources to provide niche space for more species, or in the west, there may be regional influences, say that the west is less accessible and unable to be accessed by some species. So this figure here is actually just a plot on the y-axis of the number of bird species that are present within these regions according to elevations. So these are not local data. And in order to kind of tease apart the influences of either regional or local factors which affect community structure, we instead wanted to go to a very local scale rather than these interpolated ranges. And so here's an example of a high elevation site in the Himalayas in North Sikkim. This is at 4,000 meters. And these are the boundaries of a 5-hectare plot, which Trevor kind of alluded to as well, in which we've censused all the breeding birds within that plot for both their species identities and the abundance of species within that plot. And we've done this using British Trust of Ornithology census protocols over many years and across a number of observers, and in 35 sites that's shown here from east to west across the Himalayas and along that elevational gradient. So to get an idea of what the data look like, here is the location of the plot I just showed you, and there are 11 species in that plot. These are their abundances according to this histogram, and the most common species in this plot was the buff-barred warbler showed here. So in contrast, here is a low elevation site at 200 meters, and there are 34 species present in that plot with an abundance, with seems like many rare species, and the most common species in this plot was the white-rumped shama, which is shown here. If we look across all 35 of these plots at the richness within these local plots, we get a pattern that's very similar to the pattern I showed you previously of interpolated ranges. So greater species richness in the east and more depauperate communities in the west. And as has kind of been indicated earlier or alluded to, we can attribute some of these, the local richness in these communities to local conditions ecologically. So here I'm showing you the annual precipitation from WorldClim that's aggregated across the two regions I showed you earlier, the east and the west. And we see a relationship between the patterns of high species diversity in the east associated with warm or wetter conditions. But these patterns essentially miss out also kind of an important component of kind of investigating these questions about regional and local effects, which is that we don't have information about turnover. So we know that there's potentially some local determinism associated with these conditions, but we want to know more about turnover between these different communities along the gradient and the composition of those communities, the identity of the species that, that exist within them. So just as a basic kind of introduction to our methods, to get you oriented, this is a cartoon of two communities, J and K. They share species 2. And in order to kind of compare these two communities, we can use traditional metrics, so essentially a beta diversity metric that might tell us, say, the turnover between the communities, and this metric in many cases is kind of associated with both the richness and the composition of the two communities in question. But it's a pairwise metric. And so we wanted to develop a kind of better, or a kind of more unique kind of perspective on how these communities are built based on kind of the meta-community itself. So we developed a novel method for clustering species according to kind of their co-varying abundance within the whole group of 35 communities. And we took those species, and within each plot, we can then ask how those species clusters contribute to the actual total composition of the community itself. So we'll get more into that method in a bit, but I just want to start by talking about the beta diversity. The easiest way to kind of show, I think, at a conference like this, beta diversity metrics. So again, we're looking at across all 35 of these communities. The easiest way is to connect these forest patches in a network. So this is a bipartite network. The forest patches are the colored nodes on this network, and the species are invisible nodes, and they're connecting all of the forest patches together. The colors of the patches are according to elevation, and the edges, so these edges, say, out here, are unique species only to that one community here. So the proximity of these patches together is indicating their similarity in a beta diversity space. So we see immediately that communities are clustering according to elevation, low elevation sites here and high there. And I think you can argue that high elevation sites are more clustered than low elevation sites. But we also want to know about the species composition of these communities. And essentially, this method works very similar to the way that a structure analysis might work in terms of the output. So what I'm going to show you looks a lot like a structure plot. The method itself is a bit different. But you can cluster the species according to k through n number of clusters. In this case, I'm showing you the output of the analysis when we cluster the species according to 2 clusters. And immediately, I've split it between high and low elevation, but we can see that between east and west. And each one of these bars is representative of one of our forest plots. And the contribution of each unique cluster to that plot's composition is according to the proportion of either red or green here. So you can immediately see that there's 2 sites, 2 clusters. One is at low elevation and one is at high elevation. And remember, most of these east to west grids are actually separated by over 1,000 kilometers. And amazingly, we also see that the turnover between the high and low elevation clusters within both regions is almost at the same point in the mountain. And this is despite what I showed you earlier, that there are twice as many species in the east in that location of turnover than there are in the west. So that's mind-blowing. So the next thing is to ask is what happens when we do 3 clusters. This happens to be the maximum likelihood solution. And we see, again, that there is a high elevation shared cluster between these 2 regions, but now a unique low elevation cluster in the east, which suggests potentially that there, or some kind of like line of evidence toward figuring out what these regional influences are, or that there may be strong regional influences. And so what I did was, within, say, this community here, which is entirely made up of blue, this blue cluster, I then looked, or I mapped all of the species that were present in that community in the region to kind of ask if they share some kind of other regional kind of distribution together other than just our kind of local plot. So here is that the location of that blue, that community shown here. And you can see this is a kind of map of Southeast Asia, and the red colors are where those species overlap their ranges. So this is kind of like a richness plot, but only for the species within this group, or within this local grid. We see clearly that they share a lot of overlap in Southeast Asia. If you do this for the, say, a green cluster in the west, we see that not only are they sharing a lot of Southeast Asian origin potentially, but also a great amount of shared range in peninsular India. And finally, if we look at the shared high elevation red cluster between the east and west, I grabbed this community here, and we see that this is kind of what I think of as maybe the true Himalayan group, that a lot of their range is through the Himalayas and also in western China. And we find the same is true if we look at that cluster in the west. So these two sites that I just showed you are separated by 1,000 kilometers, but here is kind of the shared range in each one of those. So potentially this is suggesting that these two sites, according to this kind of clustering method, are sharing some regional source pool of invasion. So with that, I just want to conclude by saying there are 3 distinct faunal groups in the Himalayas. That's at least what our structure, or our kind of clustering analysis has revealed. One associated with Southeast Asia, increasingly so peninsular India in the west, and this kind of high elevation cluster of species in western China. And there are strong regional, this kind of indicates that there are kind of these locally determining factors, which I showed you earlier, plus these potentially strong regional influences on community assembly. And just to conclude also, we see that turnover is strongest along elevation. So I did not show you these data, but according to the beta diversity networks that I was showing you, turnover of 1,000 meters along an elevational gradient is equivalent essentially to 1,000 kilometers of geographic distance. So with that, many thanks to my co-authors, these people for all their great ideas, and these people for all their money.